Yeah, I'd like to talk to you about today is some recent work I've done with Andrew Grozek, who is my postdoc and has now moved to University of Queensland, and also Nick Prokakis and Paolo Comaron, who many of you will know, Nick being at Newcastle and Paolo having moved to Poland in the last few years. So today I want to tell you about a crossover of the dynamical critical exponent in a two-dimensional Bose gas. So I'll start fairly simple with an introduction to sort of what I mean on critical exponents, the background, the theme, why this sort of thing, scaling laws are interesting. So universality, non-equilibrium dynamics, and domain coarsening, that will be our background today. Then I'm going to talk about how we actually describe two-dimensional Bose gases and what the open questions along the lines of those themes are. So what are the open questions that relate to the themes of universality, domain coarsening, non-equilibrium dynamics? Those two sections will probably take up the bulk of the time, and then I'll tell you about what we actually did in our results, our work, and the conclusions and future work that you might want to do. So, okay, so first let's talk a bit about universality. So universality, say at equilibrium, and as our example, we'll take the Ising model. So in the Ising model, we have simply a lattice of spins, and the spins interact with each other with some strength J, and we can write the Hamiltonian as a sum over nearest neighbors, and each spin can either be up or down. So this is a very simple model in statistical mechanics. What are its properties? So here we have the basic physics of the Ising model. So we have on the left a very cold temperature. So that's the ordered phase on the left, where neighboring spins all really want to align with each other to lower the energy of the system. At high temperatures, this interaction energy is irrelevant compared to the thermal energy in the system. And so we just basically see thermal noise. So there's just static over on the right at very high temperatures. And of course, the system has a critical point in the middle. So at the phase transition temperature Tc, the system starts to look very strange. It starts to have fluctuations on all different length scales. So it starts to appear to have some sort of fractal nature. And this is what we refer to as the universality in the model. It's worth pointing out that the image here is from a paper about the Ising model in biology. So the Ising model crops up everywhere. So when we say universality, we do mean that these models, there's an element of universality in these models cropping up everywhere as well. But the universality within a model in equilibrium statistical mechanics is near the phase transition point. So what exactly happens there? Well, at this point, as I've said, we start to see a self-similar structure. People might say this it starts to have a fractal structure. And we start to see fluctuations on all length scales, like I said before. The real important thing is that different systems, so systems other than the Ising model, for example, we're taking the Ising model as our example here, but other systems might start to display the same physics near the critical point, because the only fundamental properties that are important are the dimensionality and the symmetries of the system and any conservation laws that are at play in the system. And these determine the universality class of the model. And all the models that lie within one universality class have the same critical exponent. So once you get near the critical point, the Ising model starts to become the same as other models. For instance, Ising models where you change the interactions slightly, etc. So there's a common set of universality classes that systems fall into based on their symmetry, their dimensionality, and possible conservation laws that tell you what the critical exponents should be. So that's all very well. But what if we want to go outside of non-equilibrium dynamics and look at quenches? So now we want to sort of go from the hot image to the cold image very quickly. So there are other kinds of quenches you can do, but I won't talk about those today. So I'm going to be interested in a quench into the ordered phase. So at some time, Ti for T initial, we start with a hot system. For now, we'll just think of this thermally. So let's suppose I have a very hot system. It's at some temperature much greater than the critical temperature, and it's just sitting there nice and happy. Then at some time, I come along, time Ti, and I decide I'm going to apply a quench to the system. So I take my red hot iron bar or something, and I chuck it in a giant tank of water to very quickly lower the temperature. What are the dynamics? Well, ultimately, we've got to get back to the ordered phase because we're now at a temperature, T final. So that's TF, T final over on the right. We're at a point where we expect the, I guess you can see my pointer actually if I use the pointer. So we expect to get to a T final where there's order at some late time. So there's some time scale for this, and we expect that time scale to be pretty long. But now this is a problem in time dynamics, not a problem in equilibrium statistical mechanics. Okay, so there's two ways we could go about doing the quench. So I sort of already talked about what's on the right. I said, let's chuck our iron bar into the tank of cold water. That would be almost an instant quench, okay? So the paradigm for phase ordering kinetics is dealing with quenches like this. So we take some system and we instantaneously chuck it, a disordered configuration, straight into the system under parameters where it wants to go to the ordered phase. So the system's got to somehow work out how to order itself. The other way you could do this quench is with a ramp in temperature. And that's a related problem. And usually what's considered and has been considered very broadly in ultra-cold atoms in that context is the Kibble-Zurek mechanism. So for ramping across a second order phase transition at a finite rate and creating defects as a result. There should be some citations on the left there to the Kibble-Zurek mechanism, but I've left that out unfortunately. But I'm sure you will find some papers on it if you search for it. That's been a topic of much interest over the last sort of decade. Perhaps a little bit less interest in the phase ordering kinetics over on the right. So the classic review on this topic is by Bray, and you can see a link to that there. So that's what we're going to concentrate on in this talk. So instantaneous quenches and the system trying to order itself. Okay, so I've said phase ordering kinetics, and there wasn't really a phase other than being in the ordered phase in the context of the Ising model. So at this point is a good point, I think, to introduce some pictures from a 2D Bose gas. So the 2D Bose gas is a good example of what we mean by phase ordering kinetics. So what I'm showing in the images here is the color map with the axis over on the right is telling you the phase of the wave function, and I'm ignoring the density. Okay, and these are actual images following an instantaneous quench. So we start with an image close to the initial time of the quench, and by the right-hand image in panel C, we've got a lot further on in the quench. The black squares and the white squares with a black outline are indicating vortices and anti-vortices. So we can have these in a boson-Einstein condensate. It's a superfluid with a density and a phase. So where the phase winds at a point around by 2 pi, we get a vortex or an anti-vortex, depending on the sign. And so I'm just marking where they are. I say my postdoc Andrew has just marked where they are in these phase images. Okay. So as you can see, where the phase winds around, say, this white anti-vortex here, we've got an anti-vortex. The phase is winding around that. So what's actually happening as a function of time is in some sense very simple to describe. So the number of vortices is decreasing, and the size of the areas over which the phase is roughly constant is increasing concomitantly. And that really is the basic pattern. At some level, the rest is details, but the details are very interesting. Okay, so that's the basic picture. Now looking at the phase of a 2D Bose gas. Now, the thing that's interesting about this evolution is it can show self-similarity. So this is where scaling comes back in. So now we aren't worrying about temperature, we're worrying about time evolution. You can start to see self-similar scaling in the time evolution. So to draw this schematically, what I've done is I've just picked out a box inside panel B at some intermediate time. And you can see if I took a piece of panel B and I blew it up to the size of panel C, it wouldn't look all that different, okay? It's not exactly the same, but it has roughly the same number of vortices. The patches of roughly constant phase would become about the same size as they are in C if I just took the images from B and I blew them up. So that's the idea of self-similar scaling in time. There's nothing else distinguishing these patterns of phase and vortices from time to time. They're actually very similar if I just rescale them. Okay. So we can put that on a more mathematical foundation if we introduce something called the correlation length. So to do that, I'm going to introduce the correlation length twice. So first I'm going to introduce correlation length 1.0. So correlation length 1.0, we just look at the pictures and we say, well, what is roughly the size of one of these areas where the phase is roughly constant? So I've put in these little yellow bars, one in each figure, to give you an idea of what the sort of correlation length of these fields might be. So correlation means what's the correlation between 2 points in the field, and the correlation length is saying, well, over what distance are points well correlated? So in this case, we've got sort of a green region of about this size. The yellow bar is just saying, well, the green region's about that size. So that's about the correlation length in this system. Okay, and you can see the correlation length is growing with time. So that's the correlation length definition 1.0. Just look at the size of domains. And I'll come back to that. Hopefully I'll remember to refer back to that later when it comes up again. Okay, so bearing in mind that definition of the correlation length, I'll now talk about the dynamical scaling hypothesis. So this is really the mathematical hypothesis that sits underneath all this. So we start from some non-equilibrium initial condition, and the system pretty rapidly starts to relax and to coarsen up because it wants to smooth out its wave function. It wants to go to the ordered phase. The initial conditions will quickly be forgotten. What does that really mean? Well, it means that none of the other parameters we put in the initial condition matter anymore. So the memory of the initial condition should be gone, and the only scale that is now important is this correlation length scale. So this is the, if you like, a reformulation of what I said about the pictures looking the same, but you can just rescale them. So the only length that's really relevant to the problem is the correlation length. Okay, if that's true, then the dynamical scaling hypothesis is that this should follow a power law for some dynamical critical exponent Z. So the correlation length should grow like t to the 1 on Z. Much like in the equilibrium case, this Z, this dynamical critical exponent, shouldn't depend on the details of your initial quench. It shouldn't depend on the fine details of your model. It should depend on dimensionality, symmetry, and very importantly, conservation laws. So the dependence on conservation laws is ultimately what we're going to come back and investigate in the sort of the part of this talk that isn't background. Okay, but fundamentally that's what's supposed to happen. So the next thing to do is probably go back. And before we go any further, let's just redefine the correlation length. Now that we know what happens when the dynamical scaling hypothesis, we can define the correlation length in a more rigorous and more useful way. So instead of a correlation length, we can ask correlation, we can compute a correlation function. Okay, so I take 2 points in my wave function field, and I just work out the correlator of them. So psi1 of r, psi of r times psi star of r prime, basically. So that we conjugate the field with itself some distance away, then we plot that as a function of the distance between the 2 points I'm correlating, because we're assuming our system is homogeneous. So it doesn't matter where the 2 points are, all that matters is the relative displacement between them. And we also assume that our system is isotropic, so it's just a function of the radius. These will be roughly satisfied in our simulations later, because we'll take very large periodic boxes. So they should be homogeneous and they should be roughly isotropic. So then the correlation function G, which tells me how well correlated 2 points are, is a function of R, and of course it's a function of time as well, ought to have a scaling form if there's a dynamical scaling. And the best way to write the collapse is we take out the equilibrium correlations. So if we waited long enough, which is effectively infinite time in the sort of systems we're considering, we'd eventually get to equilibrium. There are good ways we can get to equilibrium and work out the equilibrium correlation functions. And then we can introduce a scaling function. So we're saying there's some dimensionless function f that multiplies the equilibrium correlations. And if I rescale my radius at different times by the correlation length, the system ought to look the same. So this really is just the picture of correlation length 1.0, and the correlation length grows with time. And we're adding on top the self-similarity of the pictures. Instead of looking at the pictures, we're looking at their correlation. So on the left, we have 4 times. So T1 is the earliest, T4 is the latest. And we plot the correlation function as a function of R. Okay, so I plot G over G equilibrium as a function of R at different times. And we get lots of different curves. But if dynamical scaling is working, then what should happen is what happens on the right. If I rescale my radius by the correlation length, then in fact the correlation length is the only scale in the system that's changing in an important way during this coarsening process. The curves should all collapse. So there should be a common form to all of these curves if the system is just rescaling itself in time according to the dynamical scaling hypothesis. So that's how the correlation length comes into the correlation functions. And this turns out to be the most useful way to extract the correlation length from data. So when we have data about the system, we can run this process backwards. So instead of collapsing everything nicely by choosing the right LC, I can work out what LC is by working out how I need to rescale all my times to get them to collapse nicely. So I just run this process backwards, and we can extract the correlation length. Okay, so that's the idea of that. And I just want to have a slide where I flash up, but as well as this work, there's been an awful lot of work on coarsening and this sort of dynamics, fade ordering kinetics in Bose gases in particular. So the top one's binary BC. There's also been a lot of interest in spinor gases and a lot of interest in these sorts of phenomena in polariton-driven dissipative systems. So this is like the smorgasbord of things I'm not going to talk about any further in this talk, but they are there. Okay, so a lot of interest. What are we going to talk about in this talk? Well, the 2D Bose gas. Let me go on to say something about that. So that was the themes, the non-equilibrium dynamics, the domain coarsening, universality. So why would we want to study this in just a plain old vanilla two-dimensional Bose gas? Hasn't it already all been done? That was what we thought when we started. So we were actually, me and Andrew started, we were going to do something else, which I'll probably tell you about at the end. But we realized there were open questions just for a vanilla 2D Bose gas. So we got sort of interested in answering them, and Nick and Paolo were working on the same things, similar things from a different angle at the same time. So we ended up joining forces. So let's talk a bit about 2D Bose gas, and then I'll relate it back to why there's open questions in this sort of dynamical scaling. So the first question is, if I have a two-dimensional Bose gas and I want to measure, want to model it, what description do I use? If I'm interested in these sort of phase transition type effects and dynamical scaling, the most preferred model in the literature is classical field methods, which come in sort of a variety of different versions and details, and I won't get into the detail of exactly which method and exactly what terms keeping in the equation and things in this talk. I'll try and keep it simple. But the basic idea of these sorts of techniques is that we say, well, we can capture quite a lot of information about a Bose gas if we note that the low energy modes are fairly highly occupied compared to an occupation of 1. So I ignore commutators and I treat them as classical fields. So if I impose some cutoff, so that's what my diagram is showing here, I have some space of momentum modes in my system, which I'll index with kx and ky since we're in 2D. If I cut this off at some appropriate cutoff in k space, then I can be describing a system where all the modes have a reasonably high occupation compared to 1. And so Bose-Einstein starts to look like classical Rayleigh genes, and it's just a classically interacting field. And this is a reasonable way to model it. And then what we do is basically lots of realizations with lots of random noise and average. So that's the very, very simple picture. But of course, I've got my beautiful purple circle of classical modes that I've just described how we'll treat. How do we treat the rest? So there's a nebulous the rest outside of this system. What do we do about the rest? So that leads to different flavors of classical field dynamics. So here's some different flavors. I should have called these flavors rather than descriptions. That would have been much better. Never mind. So one thing we could do with the rest is ignore it. Always my preferred first option. Difficult things, just ignore them. So we could just take the classical modes and treat them as an isolated classical system. So this, by and large, would go by the name of the projected Grosepasevsky equation. If you're careful about projecting your modes and how you do your Fourier transforms, I won't go into the details. You can think of this as just an energy conserving, norm conserving GPE that isn't interacting with any of the rest. And it's a microcanonical system, so it's got fixed energy, and and a fixed number of atoms. So that's the simplest thing. The next thing you could do is say, well, really that the rest should be some sort of thermal cloud, perhaps a bit more of a physical description. So let's chuck that in there. And the simplest way of coupling that to your low energy modes is to introduce effectively noise and damping terms. So it starts to look like a Langevin equation. You have some dissipation, you have some noise. So in what we'll look at, we'll use stochastic projected Grosseteste. Again, there are various flavors of stochastic Grosseteste equation that will do the business and give you the same physics here, maybe with some changes in the fine detail. And it's a grand canonical description because now we can exchange both energy and particles with some Bath. We could also crank up that coupling so much that the coupling terms dominate over the usual GPE terms. So the Grosseteste evolution becomes kind of unimportant. So we switch that off and we just worry about these Langevin terms. So we say there's noise and a dissipation in the equation, and that's it. So it's still grand canonical. It's effectively a Ginzburg-Landau equation, fully dissipative Ginzburg-Landau with some noise. So those are sort of three flavors. The second two are really kind of the same thing, but just cranking up the dissipation. Now, referring back to what I said earlier, of course, is the fact that the dynamical critical exponent, I said, ought to be set by fundamental properties of the system, like dimension. Well, we're just sticking to 2 here. Symmetry, we're not changing that here. Conservation laws. So the conservation laws are fundamentally different between the microcanonical energy conserving approach here and the grand canonical stochastic approach. So there is a difference in the conservation laws in these models of the dynamics. So the interesting question is, how does this then affect dynamical critical phenomena? So that was sort of what got us thinking. To say a little bit more about these methods, I won't go into too much detail, but the basic gist is that we can write one equation to model all other equations. So we write a stochastic projected Grosseteste equation. So this P here is just projecting into our subspace of low energy modes. We have the usual GP evolution term pre-multiplied by alpha. We have a dissipative term pre-multiplied by gamma, and we have a noise term dW. And what I've not remembered to put on the slide is that the strength of the noise dW also depends on gamma and T, of course, by the fluctuation dissipation theorem. So if I turned off the dissipation gamma, I'd also be turning off the noise. That's important to remember. So what can we do? Well, what are our options? So if we want to go for the microcanonical approach, we turn off gamma, no noise, no damping. We make alpha equals 1, and we have a projected Grosseteste equation that will conserve the energy. We could also model a simple growth stochastic projected equation. So we'd keep alpha as 1, keep the Grosseteste terms, and we'd have a gamma that's usually much, much less than 1 in an experiment. And I'll say more on that later. Or we could go to this strongly coupled dissipative limit, which I call model A. So I should have said this on the last slide. This gives you back the classic result from the paper of Hohenberg and Halperin back in the 70s, where they came up with universality classes for various kinds of non-equilibrium dynamics. This is the canonical example of model A. So we have some system and we just couple it with noise and dissipation to some Bath. Okay, so these are all valid approaches to describing ultra-cold Bose gas experiments. They all have different advantages and disadvantages, but the fundamental thing about all of these is they will capture the critical phenomena near the phase transition, right? because that's a fundamentally classical thing. So you get all that from the classical field theory. Obviously, they don't work all the way down to T equals 0. So these are sort of for a fairly warm, finite temperature Bose gas. But nonetheless, these have all been applied and they've all been found to be useful models. But one might expect them to have different dynamical behavior when you do a quench. So where are the open questions? Well, like I've just said, so the Model A end is very well known from back in the 70s. A bit later than that, it was determined that there ought to be a logarithmic correction in 2 dimensions to the Model A class. So when we have dissipative dynamics with some noise, we have this slight modification of the dynamical scaling. T0 is some microscopic timescale, okay, that depends on your problem. If you go to really, really long times, this looks very much like Z, a normal dynamical scaling with Z is 2. So Z is 2 is the answer, but with this logarithmic correction. So that's the most well-established result. However, if you go back to the review from the 70s, it's also well known that it's a hard problem to theoretically work out what the scaling behavior should be in the conservative case. So if you take a conservative 2D Bose gas, this is much less tractable. So there's no a priori predictions on the table for this. And this is interesting because, although I've said all these descriptions seem to work for various experiments and can be applied, normally, if you apply the stochastic approach, you'd still have a very small gamma. So it's not very strongly coupled to your bath. You're really not in this Model A limit. So there's a question of whether Model A is really the right model for these things, and what is different if conservative dynamics in these systems are different. So that's sort of what we wanted to find out. There are some subtleties around that. I guess I should not dwell on it too long, but typically you'd expect very small gamma, like I just said. When you do non-equilibrium experiments, you might have to have an effective gamma that's actually a bit higher. But still, people have generally modeled experiments with gamma as less than 0.02. So if you compare that to the scale of the GPE dynamics term, which is 1, that's still small. Okay. So there we go. So what are the previous results from this particular system? Well, this is the other thing that inspired us to investigate. So previous results fall into sort of 3 categories. So at the top, people have studied stochastic, so dissipative dynamics, so non-conservative, with various amounts of dissipation, but generally low, and found dynamical scaling with powers consistent with 2, so within the errors. So the numbers in brackets there are indicating the error, the estimated uncertainty in the last digit. So work by Paolo and Nick working on the stochastic equation, and also Carl and Gesenza. They did a study where they looked at both the stochastic equation and the conservative one. They found this for the non-conservative cases. In the conservative studies, there are sort of 2 main papers that investigated this in the vanilla 2D Bose gas. So quite a venerable paper now by Damley and others, where they measured Z was roughly 1. That should be a roughly equals sign, not an equals sign. Sorry for the typo. I don't think they really claimed Z was exactly equal to 1. Again, Marcus Kahn, Thomas Gesenza measured this in the same paper as their other result and found this one was a little bit lower, but still with an error bar that included 2. So the results still were consistent with a Z equals 2 within their estimated uncertainty. And this has also been investigated in XY model. So ignoring the density, this is a bit different, but one might expect it to be in the same universality class. A conservative XY model was found to yield something very strange, where the authors proposed a corrected form of logarithmic corrections. so corrected logarithmic corrections. So there's a lot of uncertainty about exactly what the answer to this question was. So we thought, well, let's go ahead and resolve the dependence of the scaling on the dissipation and try and investigate the origin of any changes that we find. I'm not sure how much longer I have left. Do I have another 10 minutes? When am I supposed to stop?
Yeah, I think 10 minutes is fine. So it's
excellent.
4:42. So
thanks. Always check how long you've got before you start. That's what I should have done there. Okay. So really now I've explained what we're doing. Hopefully everyone is still following and still awake. So we want to now look at the system and really investigate this in detail. As always, that turns out to be a fairly thorny numerical problem. I'll gloss over a lot of the numerical details and frustrations in just one slide. So quite a lot of text on this slide, but let me summarize. So basically what we do is we run instantaneous quenches to the ordered phase for this model, and we vary gamma, and we change alpha to also include model A, and we also run the thing with gamma as 0 and the projected coarse-specific equation to get the completely conservative case. So we've set up a whole system of simulations that do this. It's fairly straightforward to choose initial conditions when there's stochastic noise. You just start with a 0 wave function, and that's highly non-equilibrium in the ordered phase because you're grand canonical. So the particles then rush into the system and you get lots of non-equilibrium dynamics. So that's fairly straightforward. We also checked starting from a different initial condition to make sure it doesn't change. In the projected coarse-specific equation, so the conservative dynamics, of course, you can't do that. So you have to pick an initial condition that has the same energy as you want your final ensemble to have. So that sounds easy, much harder to do numerically. There's a lovely appendix you can read if you want to know how we did it. But the basic gist is we just put in a very non-equilibrium distribution of particles in momentum space. But in all cases, we choose either the temperature or the energy of the system to ensure that we're heading for the same equilibrium. So all these systems, if we run them long enough, they get back to an equilibrium where in 2D BKT physics, you expect power law correlations in the ordered phase with some, so the correlation should go like r to the minus eta for some power law eta that varies between 0 and a quarter. All our simulations are heading for the same equilibrium so that we're comparing apples with apples. And then we scale everything up to very large box sizes. We have to use graphics cards to do the PGPE computations because they take a very long time. We gather an awful lot of statistics. So most of the ensemble sizes you'll see in the results are at least 256 runs. And the box sizes are hundreds of healing lengths across. And as I mentioned earlier, we use the scaling collapse to extract the correlation length. So we work backwards. We compute the correlation function G, we do the radial averaging, then we take our correlation functions and we work out what LC has to be to have them all line up at the point where the correlations have fallen to a half. And again, we check that changing that value, the collapse threshold, we could change that to 0.4 or 0.6 and not much would change. And we're careful to try and exclude finite size effects by stopping looking for scaling when some of our simulation, once the correlation length goes over a quarter of the box size, we start to treat that suspiciously and we stop looking for scaling at that point. So we're very careful to avoid finite size effects. And we stretch the scaling window that we look for the dynamical scaling in as far back as we can while we still get a good collapse. Okay, so that glosses over months of work. what do we get as the result? So I'll start by showing you the result for a stochastic equation. So this is the non-conservative dynamics, where we're setting gamma is equal to 1, but we still have an alpha. So this is sort of, if you like, equally conservative and dissipative terms, equal dissipative and conservative terms in the Grosbeck equation. And also we have stochastic noise. So in the inset on the left, I'm showing the raw correlation functions, and they're colored by the time. So at early times, they're steeper, and at late times, they're a bit less steep, and they're darker colored. So you can see there's a whole spread there. And if we extract the correlation function by looking at what value of R do they all reach a value of f of 0.5, we can extract LC and then replot the graph, which is what's in the main figure. So we make them all line up at 0.5 and we check that they collapse over the whole range. Okay, so that's how we find the correlation length. And as you can see, the collapse is pretty good. And on the right, we then plot the correlation length as a function of time to look for the dynamical scaling. So you can see this thing going rather like a power law. At the end here, in the top right, you do see a bit of finite size effect. And the main thing that we're doing is we choose a window. So the shaded region here is the window where we actually feel we can extract the data. So we're shielded from finite size effects, and the collapse remains very good at the start of the window. And we then have a method for estimating the uncertainty in our dynamical critical exponent that we then measure, which basically means measuring subgroups of points and computing a histogram of different possible Z values that we could get. That's what's shown in sort of the histogram. So you read the histogram as saying, well, the central Z value here is 2.18 or something like this, right? 2.19. So that's what we get there. It works just as well in the conservative case. So you'll notice now that we have to run for much longer times. So these simulations are much more demanding, but we can still get to a regime where we can see reasonable scaling, okay? But we're shielded from the finite size effects at very long times. The collapse, as illustrated on the left, is still very good. The bottom inset, I should say, is just showing the corrected spectrum. So once we've measured Z, we multiply our log-log graph through by that power, so that if our power was right, we'd get a flat region. So you can assess sort of how flat in the scaling region our results are. Histogram's a little bit wider here, illustrating slightly higher uncertainties. I'll add that that was measuring the correlation length. You can also just measure the vortex number, which is a proxy for the correlation length, because vortices should be separated by roughly the correlation length, and you get very much the same results. This is a slightly less reliable method, but nonetheless, it backs up our main method. So we definitely observe dynamical scaling, we check box sizes and so on, and I can comment on that in the questions if anyone has any at the end. So what actually happens, what's our take-home message? So if we do that again and again for lots of different values of gamma, here's what we find. So the best way to read this graph, I think, for me to explain it, is from right to left. So on the right, we have this point magically over at infinity. We've extended our axis all the way there. So this is the model A, where everything's completely dissipative. The best established point of comparison would be the model A, where we expect Z is 2 with log corrections. So in green and yellow, we're showing what our results are like if you fit them with the log corrected form. And we're showing results for LC in blue and green, and NV in red and orange. You can check the shapes in the key if the colors aren't coming out right for you. But the basic gist is we expect the LC measurement is the best. And for model A, that's bang on 2, which is exactly what we expect. So we're agreeing with the end where the result is known, which is always nice. You'll see that systematically, if we use the vortex number, we get a slightly higher answer with a bigger uncertainty as a rule. So the red and the yellow points just really show that. And you can see that there is this crossover in the exponent. So as we dial gamma down, 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 our measurement drifts away from being consistent with Z as 2. There's no reason a priori to expect the log corrections to apply in this regime. So that's why we also plot the uncorrected result, if you like. So log corrections are expected over on the right, but they aren't necessarily expected over on the left. So we just fit a raw power law. In practice, the quality of the fits is either similar or the power law is better. And our main result, I guess, is this crossover that happens around gamma is 10 to the minus 1. So the exponent drops and drops, and it becomes inconsistent with 2 to within as well as we can measure it. So our final measurement comes out around 1.7. The error bars are estimated based on statistical errors. We also consider our systematic errors, but all our error consideration suggests that we're reasonably confident that this is not overlapping with 2. So it's a nice trend. It's also worth remembering that completely different codes generate the dynamics in different regimes as well. So there's even a check between different numerical methods being used here. So the method used for the SPGPE results is independent of the PGPE, but they join up. So we really seem to see a crossover.
Tom, sorry to interrupt you. You are almost 5 minutes past 2 to 5, so it's up to you how you want to. Well,
that's
if you want
fine.
to take questions,
I can finish this off in about a minute, I think.
Okay.
So, yeah. Sorry, David. I will gloss over this somewhat, but we also considered why this is the case. We returned to the classic argument for why Z is 2 in the sort of default picture in this system, which is that the speed of the domain growth is just given by the vortex velocity. So this is this picture of the domains just being the distance between vortices again. So maybe the vortex velocity is just governing domain growth. So you simply say LC by dt is just the vortex velocity. Then we say, well, the vortex velocity goes like 1 over the vortex spacing, but with some mobility correction. Okay. It turns out if you put in power law mobility correction, you can end up with a Z that's 2 minus epsilon if we put in a power law mobility. Thanks to Tapio's similar for that suggestion. We were puzzling over this, and he actually suggested that in a conversation we had with him about our preprint. So we tried that out, and there's some reasonable evidence that this works. I'll just mention the right-hand graph here, which I think captures what we do to test this. So the earliest time is over on the right-hand side of this graph up in the top right corner. We take our PGP simulations, we pull out the vortex positions, and we put them in a pure point vortex model with the same sort of parameters that ought to match roughly the parameters in the PGP. If we run the point vortex model forwards in time from there, it goes straight back to Z is 2. Okay, so whereas if we track the vortices in the PGPE model, they behave differently, and we get a different power law that's consistent with the Z that we measure. So it seems that it's vortex dynamics that are happening in the full field. So when there's sound waves and such in the field as well, that don't happen if we just take a pure point vortex model. So that's about as far as we got with explaining why. So more work to be done on that. But I guess I will just wrap up there in that case. So our results are consistent with model A where we expect them to be. We see a decrease in dissipation, a decrease in Z as the dissipation drops towards the conservative limit. To within our error estimated uncertainties, the exponent in the conservative limit is different from 2, and we think this is something to do with vortex dynamics that needs further investigation. So I'll stop there. Sorry for running over. I hope everyone's still awake. Happy to take questions if there are any.
Thank you, Tom. Any question for Tom? Just unmute yourself or write it in chat. So we have a question, Shinichi Tsunami. I hope to pronounce it well. What is the transition that is crossed by the quench? If it is BKT transition, what is the effect of thermally activated vortices to the defect dynamics? I think that you're muted, Tom.
I am, sorry. Yeah, so effectively, yes, this is the BKT transition that's being crossed. So thermally activated vortices aren't an issue here because we're crossing rapidly into the ordered phase. So our initial conditions contain vortices that I guess you could what's the way of putting this? Our initial conditions are not thermal initial conditions. So we don't take a thermal state from very high temperature and then quench that. So like I said, we're either taking psi as 0 state, which is then fed with noise, so it's very non-equilibrium, or we take something that's very non-equilibrium in the PGBE. So we're taking something that's not in equilibrium at all and then quenching it straight to below the BKT transition. So I wouldn't say there's a role of thermal vortices directly in this at that level. Does that answer the question, or is there more I should say?
Yes, thank you very much.
Okay, thanks.
I can see somebody that has a hand, I think, a lift.
Yes, thanks. Very early on in this talk, you mentioned the Kibble-Zurek mechanism. And well, I understand that much better than what you have been talking about today. It's been very interesting though. But I'd like to ask that if you take the Kibble-Zurek mechanism towards instantaneous, well, I mean, that theory gives you infinite vortex density eventually. And so therefore something will yield. And I'd like to ask whether this quench dynamics is what they're actually going to replace Kibble-Zurek in that limit, or how should I think about this?
Yeah, it's a bit of a subtle question. So it depends a bit about what you're trying to get from the Kibble-Zurek description, would be my interpretation. I think perhaps some opinions do vary on this, but my so usually with the Kibble-Zurek, you have some quench that happens over some time, and at some point the system stops being able to react adiabatically to your quench, and it goes into the impulse regime, and then it comes back out again. Does that make sense?
Yes.
Yeah, okay. So then once you're out of the impulse regime again, you've got some fixed density of vortices, but you might not yet be in equilibrium. So the density of vortices you have, say, after the phase transition is predicted by the Kibble-Zurek prediction for the defect density. But then in some sense, you go into this phase ordering kinetics if you just keep pushing the time longer, I think. So if you keep pushing for longer and longer times compared to the ramp, if the ramp is fast, then the part you normally focus on in Kibble-Zurek, which is like how many defects do I create through the ramp, becomes not the interesting question, and the post-quench coarsening dynamics becomes the interesting question. And I think that's sort of that's the interplay between these two things. So if you did a very, very short quench in Kibble-Zurek, you'd see an awful lot of defects, but they wouldn't hang around very long because they'd start to coarsen by something that's more like this process. So I think that's certainly the way I would think of it. Does that help?
Yes, thanks. Because my approach angle is that we did some air-drill measurements in helium-3 with half quantum vortices, and now they get stuck. So you see the more or less the initial density, which becomes frozen. And
right, okay.
so that's well, it's a completely different, well, I mean, non-dynamics, if you like.
Sure, right, okay. That's interesting. We I didn't have time to say, but the question that we were working on before we did this was about having, how does having potential defects in there affect this coarsening? So that's very interesting.
All right, thanks.
So I just want to say I'm happy to take more questions and continue the discussion. But for those of you that have to go, because maybe you've got other commitments, I just want to advertise that next talk is going to be in 2 weeks, and it's going to be given by Dr. Arkady Soldatov on polar phases in helium-3 in nematic aerogel. So then going back to the question, I think next one probably was Haider, and then we have a question by Andrew. But Haider, if you want to unmute yourself.
Hello, can you hear me?
I can, yes.
Yeah, okay. Thank you for the talk, Tom. It was quite a nice talk. I just wanted to ask about, you commented a little bit about Thomas Gassenser's work. I mean, one of the things that I've extracted from reading that work is that, at least in the conservative case, focusing on the conservative dynamics, there are two different regimes. Early times, you get, well, he claims that the scaling is something, for the correlation length is something like t to the fifths, whereas at late times, I think it becomes t to the half. And the explanation is that as you build up the thermal cloud due to dynamics and vortex annihilation, it becomes more like a dissipative dynamics at late times. And so the question, I guess, is, I mean, are you sort of careful enough to check that you are fitting into one regime and not sort of trying to do a fit across two different regimes? That's one question. And the second question is just, what's the typical number of vortices you have towards the end of your simulation? I'm wondering how important a fluctuation affects.
Okay. Yep. So on the first question, this is a sort of a point about what's in the paper by Carl and Gassenser. So they try quenches from different kinds of initial conditions. So there are the initial conditions that sort of lead to some vortex clustering, and where they see the sort of glassy, very slow power laws. But there were also ones where they just quench from random vortices, basically. Does that ring bells?
Yeah, so I guess you're saying then that your simulations would coincide more with the random vortices, not the clustered cases.
Precisely, yeah. So we're just comparing them to what they measure for the sort of apples to apples comparison of just random initial vortices. So their random vortex initial condition is much closer to the sort of initial condition that we have. Although I entirely agree, it's not precisely identical. But we have varied our initial conditions a little bit, so I haven't put that in the talk. But we've messed around with varying the initial conditions, and we find it isn't making a huge difference. But yes, absolutely. If we started from their other initial conditions, then there would be two different timescales and so on. But really, all we do is we just wait to see some scaling, and it goes straight to the thermal scaling, effectively.
Right.
Yeah. There was a second question, which was the number of vortices. Not very many by the end. vortices per healing length. So roughly speaking, I'm not going to give you an exact number, but roughly speaking, if you take 10 to the minus 4 on the right-hand graph, that is something like 9 vortices per box, just scaling up from, so the size of the box is 300, so 300 squared. Yeah, I think that's right.
So the plot
we've
that
still
you're showing here, the blue plot, is that an ensemble averaged or not?
The blue plot is, it's 256.
Okay, so that's why it's
sample.
fairly smooth. It doesn't have a lot of fluctuations on it.
Okay. That's right. So we are down to a discrete number of vortices by sort of the end of the scaling window, but we should still have about more than 10, I think. But like you said, it's all ensemble average, so we don't worry terribly. It does eventually turn into noise once you get down to sort of 1 vertex per simulation.
Sure. Okay.
Well, 2.
Yeah, that answers my question.
Yeah.
So I think that our next question is from Luca. Do you want to unmute yourself?
Could you say something about the finite effects? Why are they more relevant at long time when the correlation length is small?
So there are 2 things I can say about finite size effects, I guess. So the first is, what you observe is that you start to lose the scaling at long times. So where are we? Let me share a different window. That will help. Okay. Somehow this is taking a very long time to scroll through, but give it a second and we'll get there. So this graph figure 7, you can see we don't do any rescaling. So we just plot the correlation length against time for various different box sizes. And you can see that there's a common trend, but then, so the solid symbols turn into dots when you start to deviate away from, well, looking at the graph, they appear to deviate away when the power law appears to deviate away. But really what we're doing is just cutting it once one of the trajectories, once one of the trajectories gets to a correlation length of L over 4, which obviously is when you're starting to have the correlation length approach closer to the box size. So when the box size is pretty small, you basically don't notice it so much. There's also, where are we? So you can also check how the value of Z changes as you scale the box size.
So this correlation length, LC, becomes very large at large time.
Yes. So so the correlation length becomes very large at large time, but it's obviously it's capped above by sort of half the box length.
Yeah. So it's not related to the actual correlation length of the ground state, which is the healing length.
You mean the healing length as in size of a vortex core, say?
Yes, which is roughly the distance at which I expect two particles to be correlated in the ground state.
Okay, no, yeah. So this is a phase. This is a correlation in the phase length. So, like, if you think about the ground state in the classical field description, the phase of the field is correlated over long scales. So this is a different correlation length to that.
Mm-hmm. Thanks.
So I think the next question is from Gary.
Yeah, I had a couple of comments. First of all, on the log correction, you wrote that the dynamic exponent, the dynamic correlation length goes as t over log t to the 1 over z power. I think that log t really does not appear for superfluids. It only shows up in the XY model simulations. The XY model is not in the same universality class as superfluids. That's actually not well known, but there is a paper by Bray where he explores that and shows that for the XY model, that log correction should be there. But for a superfluid, we found in our Fokker-Planck equation for Kosterlitz Thales that log correction is not there for the case of a superfluid. A second comment is actually when you quench a system of vortices, what we find is that the vortices basically disappear because there's an entropy cascade. It's actually this turbulent entropy cascade, which is the reason that the vortices disappear. The vortices and anti-vortices attract each other and they eventually annihilate. And that process is, in fact, the entropy cascade, which I think you and your colleagues in Australia did the simulations on that. So it's interesting that you get this cascade in the quench. It's how the quench evolves is through this turbulent current.
Okay. Thanks for the comments. I'm also sorry I didn't mention the bit of the paper where we compared to your some of your results. I didn't realize you would be in the talk. So on the XY model, I think so there are, one can find a few different ways of writing and arguing for the log corrections in the literature. I'd be grateful if you know which Bray paper it is where he's explicitly checking the difference between the XY model and the superfluid. That would be helpful.
Yeah, I can send you that paper.
Yeah, thank you. Yeah, I haven't quite picked up on that point. With the entropy cascade, I'm not sure that we are seeing an entropy cascade here.
Oh, it's there. It's there.
Okay, I think we probably disagree on that point.
Okay, I have a recent paper in Physical Review Fluids on the entropy cascade and how it relates to the dynamics of the quench case. I'll send you that paper too.
Okay, thanks.
I don't know if Shinichi Tsunami has another question.
Yeah, can I ask another one?
Please.
Probably this is an experimentalist question, but do you think it is possible to study this in cold atom system? Is this too finite size to study such phenomena, or is tens of micrometers of size enough to study this?
Yeah, that is a good question. I think it would be tricky with current experiments, but I think well, there's two issues. I think system size is probably the main issue, right? I think really to get good measurements, you'd need hundreds of Healing lengths. And that is tricky, but it's probably not outside the realms of possibility. The thing that is a bit tricky is that really in experiments, you can't dial gamma like we do in this work. So you couldn't say run it as model A and then change and run it as something else. You'd be measuring you'd be measuring what Z you get in the experiment that you do. So what would be really nice is if someone could make a BEC that would say 150 Healing lengths across, so they had some sort of hope of doing this, do some very simple experiments just driving the BEC to see if they can measure the dissipation, gamma, get a good measurement of gamma, and then get a good measurement of Z and see how they line up compared to our predictions.
It seems quite challenging.
Yes.
Thank you very much.
That's why we did it numerically. That's
I don't know if Haidar still has some questions that he would like to ask. I can see your hand rising, but
no, I probably just
okay.
Down lower.
Can I ask a quick question, Tom? So, well, I've got many questions, but one of the things that is not clear to me. So you said that, if I got it right, that the micro and grand canonical simulation, they have different conserved quantities, conservation laws. Yeah. Can you explain a bit more on that? Because I thought that in equilibrium, then you will get essentially the same statistical steady state in both cases. So why do you say that there are different conserved quantities?
It's pure, well, so in equilibrium, how to put this? So in equilibrium, you can choose a temperature and say the grand canonical approach, choose the temperature and the chemical potential so that you get the same density and the same energy.
Absolutely. As
you would in the microcanonical, but you only get those on average. Mm-hmm. So the fluctuation is small, and I guess it becomes vanishing in the thermodynamic limit, but our systems don't really approach that limit too well. And you would still have different there's still a difference between having fluctuations, even if they're infinitesimal, and having a completely fixed energy. So really it's in terms of how say the vortices move. So if you just think of a point vortex model, the completely conservative case is for opposite sign vortices to move in parallel lines, and then when you turn that off, they start to move towards each other once you put the dissipation. So it's really that.
Yeah, I think I
does that answer the question?
Yeah. It was just a clarification on that. Yeah, thank you.
I mean, I guess if I can say one more thing on it, the thing would be that you expect as you turn the dissipation down, these things ought to join up rather than there be a sudden change. From very, very small dissipation to zero dissipation. I wouldn't expect that to be a sharp change, and we see that it's not.
Yeah. Well, thank you. Are there any more questions? So if not, I'll thank Tom again for everyone, or if you just want to unmute yourself to thank Thomas or to clap your hands. And yeah, thank you for the interesting talk, and thank you all for collaborating to the interesting discussion later on with many questions. So we will have our next webinar in 2 weeks' time, the 9th of March, again at the same time, so from 4 to 5 UK time, PM. And as I was saying, Dr. Arkady Soldakov from Kapitsa Institute for Physical Problems in Moscow is going to give a talk on polar phases in helium-3 in nematic barrier gel. So see you in 2 weeks then. Thank you, everyone.